Okay, so in this problem, we kind of have two really distinct parts. The first part, we're kind of going to work backwards with where we know a block ended up to figure out how much a spring had to be compressed for that to happen. And then in the second part, we're going to kind of redo the problem, but we're going to add another block and talk about collisions, basically. So the first part, we know we've compressed a spring, we've launched a block off a tabletop, and we know where it hit the ground. And from that information, we want to determine how far the spring was compressed. So the first step to doing that is to figure out how long the block is in the air, from when it leaves the table to when it hits the ground. And so this is another example of something that illustrates the independence of the coordinate directions. So the amount of time it's in the air is dependent only on the height, the vertical height that it falls, not the horizontal distance that it travels at all. And so we can use this kinematics equation to solve for it. Now, since we're working vertically, I'm going to kind of rewrite this with the more proper variables that we're used to, right? This is the one on the equation sheet you want to find. So the first thing, right, this x, is how far did we go? When we went down a height, 0.80 meters, that's what it says. We went down that much. Where did we start? 0. How fast were we moving in the vertical direction only, right? Because we're describing vertical stuff here, we care about this vertically only, which is 0. And then the acceleration is negative g, right? So now we can substitute it and sort of fully solve it. Negative 0.80 equals negative 1/2. That is terrible half. Times 9.8 times t squared. Right, so the negatives will go away. We'll get t is the square root of 2 times 0.80 divided by 9.8. So 2 sig figs, and we get an answer of 0.40 seconds. Right? So this tells us the block is in the air for 4/10 of a second. The second question then is, how fast must it have been moving when it left the table? And here's where we care about the horizontal distance part. We know it was in the air for this amount of time. We know it traveled a total of 1.2 meters. And we know that there's no horizontal acceleration in free fall. So we can put this together, right, use that kinematics equation again, but with some slightly different simplifications. So, how far did it travel? That's this. That's 1.2 meters. Where did it start? At the origin. How fast was it moving initially? Well, that's what we want to find. And what's the acceleration? 0. So now we can sort of clean that up. Actually, I'm going to do one more step before I substitute this next step. So, and how long did it take? Well, we just calculated that, 0.40 seconds. So we can plug that in, and we get that V naught is 1.2 divided by 0.4, or 3.0 meters per second, right? It must have been moving that fast to cover the horizontal 1.2 meters in the 0.4 seconds that it had before it hit the ground. Okay? And so finally, our tabletop is frictionless, and so we want to figure out how far the spring had to be compressed to give it this velocity, right? And that's an energy conservation statement. We're going to convert spring potential energy into kinetic energy of the block. Right, so that is, right, this energy is conserved, there's no friction or anything like that. So initial energy is the spring's energy. And our final energy is kinetic energy. right? And it's not moving up or down when it's attached to the spring, so we don't have any gravitational potential to deal with. So we're going to get x, we can cancel the 1/2, equals v square root m over k. And we know the mass of the block, and we know the spring constant, and we just found the velocity. That's 650 there, if it's not very legible. So you punch that into your calculator, you get 0.24 meters. And so that tells us that if we compress the spring by 24 meters, then it gets up to a speed of 3 meters per second when it leaves the spring, and therefore it travels 1.2 meters horizontally in the time it takes it to hit the ground, right? And so that's kind of the 1/2 of the distinct question, parts A through C. So part D. Now we set it up exactly the same, but we put another block, an identical block, at the edge of the table. So when the first block, block A, is launched off the spring, now instead of just block A sliding off the edge and hitting the ground, it has to hit block B first, stick to it, and then they fall off the ground together. So, important keywords, right? It's a collision, and it's a collision where things stick together. That tells us that it is an inelastic collision. So, we know it's a collision. We should always start with momentum conservation, no matter what. So, let's do that. So, momentum conservation. Right, so we want to figure out how fast the combination of blocks are moving after the collision. And we know what VI is. This has to be the same 3.0 meters per second, because we're told we compressed it the same amount as we did before. Right, so that's the same. So we can get that V final, where this is the velocity that the combination of blocks leave the table with, is going to be the initial is that. And so this ratio right here, this fraction, is like 4 over 4 plus 4, which is just 1/2. So that's going to be 1.5 meters per second. So now instead of leaving the tabletop at 3 meters per second, we leave the tabletop at 1.5 meters per second. However, we have not changed the height of the table, so the amount of time it takes for it to hit the ground does not change. So now the distance we travel is just 1.5 times the same amount of time, which is now half the old distance, right? 0.60 meters. Right, so we left the table moving half as fast, so we cover half the horizontal distance. Makes sense. Okay. So that's part D. Part E is a justify, explain, and write part. And so we're asked for a system of the spring, both blocks in the table, and we're asked to compare how the total mechanical energy of the system after the blocks stick together is related to the total mechanical energy of the system when you've pulled the spring back and they're just about to let it go. And so this one is actually quite simple, as long as you remember what that type of collision where things stick together is, because that right there is sufficient justification. So I would say that we know that E2 is less than E1 because in an inelastic collision, right, in inelastic collisions, energy is lost. And that's it. That's all you have to do. Right? You have to remember that when they say the keywords sticks together in a collision, that means inelastic. And in inelastic collisions, energy is lost. That's it. Okay? And that fully justifies it. You can be more precise if you want. You could explain what happens to the energy. Well, when the blocks stick together, the molecules are deformed, bent, they're heated up a bit, anything like that. That's true. That explains this in more detail. But you don't have to. All you have to do is reference that it's an inelastic collision. Maybe you'd say it's an inelastic collision because they stick together. That defines an inelastic collision, but anything kind of related to that. And you could also simply calculate the energy before and after. Right? We have this speed, we have the speed of block A before the collision. We could calculate the energy before, the energy after. We could justify it by saying, well, here's the actual numerical values. That would also be acceptable. And so that is the full solution to this one.